Hey guys, welcome back. Tonight, we will be embarking on an extraordinary journey to one of the most fascinating and alien environments in our solar system. A world where the very ground beneath your feet is made entirely of water ice, where the laws of physics create phenomena that would seem impossible on Earth, and where the boundary between liquid and solid becomes. You'll discover how ice can behave like rock, flow like rivers, and create landscapes more alien than anything science fiction has ever imagined. This is the story of what happens when you find yourself exploring a planet where ice isn't just frozen water, but the fundamental building block of an entire world's geology, weather systems, and even its potential for harboring life in forms we're only beginning to understand. If you like the content and want to support the channel, be sure to subscribe. You stand on the observation deck of the research vessel Crystalline Explorer, watching through the reinforced viewport. As your destination gradually grows larger against the star-filled backdrop of space, the planet before you, designated Glacialis Prime, appears as a brilliant white sphere, marked with swirling patterns of blue and silver that shift and dance across its surface like living artwork. You feel a mixture of scientific excitement and nervous anticipation as you realize you're about to become one of the first humans to set foot on a world composed almost entirely of various forms of water ice. Your mission briefing indicated that Glacialis Prime orbits a red dwarf star at the perfect distance to maintain surface temperatures that keep water ice in multiple phases simultaneously. You've studied the preliminary data, but nothing could have prepared you for the alien beauty of this frozen world as it fills more and more of your field of view. The planet's surface reflects sunlight with such intensity that you need to adjust the viewport's filters to prevent eye damage from the brilliant glare. Dr. Elena Vasquez, mission's chief planetologist, joins you at the observation window and points out the various geological features visible from orbit. You can see vast mountain ranges composed entirely of water ice, their peaks reaching heights that would dwarf Earth's Himalayas. Between these frozen ranges lie expansive plains where different types of ice create a patchwork of colors ranging from crystal clear to deep blue to almost black, depending on the molecular structure and density of the ice formations. Hi. You feel amazed as Dr. Vasquez explains that the ice on Glacialis Prime exists in at least 17 different crystalline phases, many of which are impossible to maintain under Earth's atmospheric conditions. The planet's unique combination of pressure, temperature, and gravitational field has created an environment where water molecules arrange themselves in ways that produce ice with properties ranging from diamond hard to almost liquid soft, creating a geological diversity that rivals any rocky planet. The ship's atmospheric analysis systems report that Glacialis Prime possesses a thin but stable atmosphere composed primarily of water vapor, with trace amounts of methane and carbon dioxide. You realize that this means the planet has active weather systems involving various forms of precipitation. Not just snow, but multiple types of ice crystals that form under different atmospheric conditions and fall to create the complex surface patterns you're observing. As your ship enters the planet's upper atmosphere, you feel the subtle vibrations of atmospheric entry, but the descent is remarkably smooth due to the thin atmospheric density. Through the viewport, you watch as wisps of ice crystals stream past the ship's hull. some forming intricate patterns as they interact with the vessel's electromagnetic field. The ice crystals are so fine and numerous that they create aurora-like displays of scattered light around your ship. You observe that the planet's surface features become more detailed and alien as you descend through the atmosphere. What appeared from orbit to be smooth ice plains resolve into incredibly complex landscapes of ice formations unlike anything found on Earth. You see towering spires of blue ice reaching toward the sky like frozen trees, vast canyons carved by flows of semi-liquid ice, and geometric patterns that suggest crystallization processes operating on geological timescales. The landing sequence brings you down in a relatively flat area that the orbital surveys identified as composed primarily of hexagonal ice, the same crystalline form found in Earth's ice cubes, but here, existing as the bedrock foundation of an entire world. You feel the ship's landing thrusters engage, creating small clouds of sublimated ice vapor that swirl around the landing site like ethereal fog. As you prepare for your first EVA on this frozen world, you don your specially designed environmental suit, equipped with heating elements, crampons for traction on ice surfaces, and sensors to monitor the various types of radiation that ice can either absorb or reflect. You feel the suit's life support systems activate, creating a comfortable microenvironment that will protect you from the planet's sub-zero surface temperatures and low atmospheric pressure. Stepping through the airlock onto the surface of Glacialis Prime, you feel the crunch of ice crystals beneath your feet, and immediately notice that the surface has a different quality from any ice you've experienced on Earth. The hexagonal ice beneath your boots is incredibly hard and dense, compressed by millions of years of atmospheric and gravitational pressure into a substance that rings like metal when you tap it with your geological hammer. You look around at the alien landscape surrounding your landing site and feel overwhelmed by the strange beauty of this frozen world. The ice formations stretch to the horizon in every direction, creating a vista that seems to belong more in a crystal cavern than on a planetary surface. The low-angle sunlight from the red dwarf star creates prismatic effects as it passes through the various ice structures, filling the air with countless tiny rainbows. Dr. Vasquez's voice crackles through your suit's communication system as she describes the initial surface readings from her instruments. The ice beneath your feet is approximately negative 40 degrees Celsius, but the thermal readings show significant variation across the landing site due to different ice phases having different thermal conductivity properties. You realize that even this small area contains a complex thermal landscape invisible to your eyes, but critical to understanding the planet's geology. You begin your first surface traverse, following a planned route that will take you to several different ice formations within a few hundred meters of the landing site. As you walk, you feel the ice surface changing beneath your feet, sometimes hard and brittle, sometimes with a slightly yielding quality that suggests different crystalline phases or varying degrees of compression. Your first sampling target is a formation that appears to be composed of cubic ice, a phase of water ice that exists only under specific pressure conditions not found naturally on Earth. You feel fascinated as you examine the formation through your suit's magnification visor, seeing that the cubic ice has formed geometric patterns that look almost artificially constructed, but are actually the result of natural crystallization processes operating under alien conditions. Using your sampling equipment, you carefully extract a specimen of the cubic ice for later analysis. You feel surprised by how difficult the extraction proves to be. The cubic ice is harder than granite and requires diamond-tipped tools to penetrate. The sample, once removed, begins to undergo slow phase changes in your suit sample container, gradually transforming from cubic to hexagonal ice as it equilibrates to the slightly different pressure conditions inside the container. You continue across the ice field toward a formation that orbital imagery suggested might be composed of amorphous ice, a non-crystalline form of solid water that exists in a glass-like state. As you approach the formation, you feel amazed by its appearance. It looks like a frozen wave of perfectly transparent water, as if the ocean had been flash frozen mid-motion, and then sculpted by geological forces over millennia. The amorphous ice formation proves to be even more alien than you anticipated. When you touch it with your gloved hand, you feel it yield slightly under pressure, then slowly spring back to its original shape like some kind of frozen rubber. Dr. Vasquez explains through the communication system that amorphous ice can exhibit viscoelastic properties, behaving as both a solid and a fluid depending on the timescale and magnitude of applied stresses. Your instruments detect that the amorphous ice formation contains trace amounts of dissolved gases, primarily carbon dioxide and methane, which may have been trapped during the formation process millions of years ago. You feel excited by this discovery because it suggests that the ice formations on Glacialis Prime might preserve atmospheric samples from the planet's distant past, potentially providing a record of environmental changes over geological time. As you collect samples from the amorphous ice formation, you notice that your activities are creating small fractures that propagate through the ice with fascinating patterns. The fractures move slowly, taking several minutes to travel distances that would be covered almost instantaneously in normal ice, suggesting that the amorphous ice has internal stress distributions and failure mechanisms completely unlike those of familiar crystalline ice. Your next target is a towering spire of what appears to be high-pressure ice, possibly Ice 6 or Ice 7, phases that require pressures thousands of times greater than Earth's atmospheric pressure to form. You feel puzzled about how such high-pressure phases could exist at the planet's surface until Dr. Vasquez suggests that they might have formed deep in the planet's interior and been brought to the surface by geological processes analogous to the volcanic activity that brings deep rocks to Earth's surface. As you approach the high-pressure ice spire, you notice that it's surrounded by a field of smaller formations that appear to be undergoing slow phase transitions as they equilibrate to surface pressure conditions. You feel like you're watching geological processes in slow motion as the ice structures gradually transform from high pressure to low pressure phases over timescales of minutes rather than the millennia such processes usually require. The high-pressure ice spire itself is a marvel of natural architecture, rising nearly 50 meters into the thin atmosphere with a crystalline structure so perfect it looks like it was grown rather than formed by geological processes. You feel dwarfed by its scale and beauty as you stand at its base, looking up at ice formations that gleam like precious gems in the alien sunlight. Your sampling attempts on the high-pressure ice prove challenging because the material is undergoing continuous phase transitions that make it difficult to maintain stable samples. You watch in fascination as pieces of Ice 7 that you chip from the spire slowly transform into Ice 6, say, then into ordinary hexagonal ice. Each phase change accompanied by subtle changes. During your work at the spire base, you notice movement in your peripheral vision and turn to see what appears to be a flow of ice moving slowly across the landscape like a river. Dr. Vasquez confirms that you're observing a glacier of plastic ice. Ice that has been heated by geothermal processes to temperatures just below its melting point, allowing it to flow like extremely thick liquid while remaining technically solid. You decide to investigate the plastic ice flow, carefully making your way across the frozen terrain toward what might be the closest thing to a river that exists on this ice world. As you approach the flow, you feel amazed by its appearance. It looks like thick, translucent syrup flowing in slow motion, carrying with it fragments of other ice phases that tumble and rotate in the viscous current like pebbles in a stream. The plastic ice flow is approximately 10 meters wide and flows at a rate you estimate to be several centimeters per minute. You feel mesmerized watching the slow-motion river of ice carry various frozen debris downstream, creating a scene that's simultaneously alien and strangely familiar. The flow appears to originate from a distant source that might be a geothermal vent or area of subsurface heating. You carefully approach the edge of the plastic ice flow and insert temperature probes to measure its thermal properties. You feel surprised to discover that the flowing ice is only a few degrees colder than the melting point of normal ice, but its pressure and the presence of dissolved impurities have lowered its melting point enough to maintain the fluid-like behavior at temperatures that would freeze normal water solids. Your instruments detect that the plastic ice flow contains dissolved minerals and organic compounds that have been leached from the planet's interior rocks and ice deposits. You feel excited by this discovery because it suggests that the planet has active geological processes that could create the chemical gradients and energy sources necessary to support exotic forms of life adapted to ice world conditions. As you collect samples from the plastic ice flow, you notice that the material has a complex internal structure with layers of different compositions and properties. Some layers are almost transparent, while others contain suspended particles that give them various colors and optical properties. You realize that each layer might represent different episodes of flow activity, creating a geological record of the planet's thermal history. The flow carries occasional chunks of exotic ice phases that you haven't encountered elsewhere on the planet's surface. You watch pieces of what might be Ice 8 or Ice X, ultra-high pressure phases that normally exist only in planetary cores, tumble slowly past in the viscous current. You feel like you're observing the planet's deep interior being brought to the surface through geological processes unique to ice worlds. Your exploration continues toward a formation that orbital imagery identified as potentially being composed of clathrate ice, a cage-like structure where water molecules trap other compounds in crystalline frameworks. You feel anticipation building as you approach this formation because clathrates can concentrate and preserve complex organic molecules, potentially serving as natural laboratories for prebiotic chemistry. The clathrate ice formation appears as a field of bubble-like structures frozen into the surface ice, creating a landscape that looks like frozen foam or solidified sea froth. You feel fascinated by the regularity of the structures, which suggests that the clathrate formation process created highly organized patterns through self-assembly of water and gas molecules under specific pressure and temperature conditions. Your instruments detect that the clathrate structures contain significant amounts of methane, carbon dioxide, and more complex hydrocarbons trapped within their crystalline cages. You feel excited by this discovery because these trapped compounds represent a concentrated source of organic chemistry that might support exotic metabolic processes adapted to the ice world environment. As you sample the clathrate ice, you notice that the structures are metastable. They maintain their cage-like organization under current conditions, but small disturbances can cause them to collapse and release their trapped compounds in small puffs of gas that create temporary clouds in the thin atmosphere. You feel like you're handling chemical time bombs that preserve ancient atmospheric compositions and organic chemistry. The released gases from disturbed clathrate structures create temporary local weather phenomena as they interact with the planet's atmosphere. You watch small clouds of methane and carbon dioxide form around your sampling sites, creating localized pressure and temperature changes that affect the phase behavior of nearby ice formations. You're witnessing the complex feedbacks between chemistry, physics, and meteorology that operate on ice worlds. Your suit's atmospheric sensors detect that the clathrate decomposition is creating temporary pockets of enhanced atmospheric density around your worksite. You feel the subtle changes in atmospheric pressure as your suit's systems compensate for the varying external conditions, and you realize that the planet's surface is more dynamic and chemically active than initial surveys suggested. Dr. Vasquez, direct your attention to seismic readings that suggest geological activity beneath the planet's ice surface. The data indicates that Glacialis Prime has active tectonics involving the movement and deformation of thick ice sheets over a rocky or metallic core. You feel amazed as you realize that this ice world has plate tectonics analogous to Earth's, but operating through mechanisms involving the flow and fracture of various ice phases, rather than rocky materials. You observe evidence of tectonic activity in the form of pressure ridges where different ice sheets have collided and been forced upward, creating mountain ranges of compressed and deformed ice. The ridges show clear signs of ongoing deformation, with fresh fractures and displaced ice blocks indicating that the geological processes are currently active rather than ancient history. The tectonic activity appears to be driven by tidal forces from the planet's orbital dynamics and internal heat sources that might include radioactive decay or gravitational heating from core compression. You feel awed by the realization that this frozen world has an active geological engine that continuously reshapes its surface through processes operating on both human and geological timescales. Your exploration takes you to an area where recent tectonic activity has exposed subsurface ice layers with compositions and structures different from the surface ice. You feel like an archaeologist examining geological strata, but instead of rock layers, you're looking at the history of ice formation and deformation, preserved in crystalline structures that record millions of years of planetary evolution. The exposed subsurface ice layers show evidence of different environmental conditions during their formation, with variations in crystal structure, dissolved gas content, and trace element concentrations that reflect changes in the planet's atmospheric composition and thermal state over geological time. You realize that you're looking at a natural archive of the planet's climate history preserved in ice formations. Some of the subsurface ice layers contain what appear to be organic compounds more complex than those found in the surface clathrates. You feel your pulse quicken as you realize that these might be biosignatures, chemical evidence of biological processes that operated in the planet's subsurface environment where liquid water might exist under pressure. Despite the surface temperatures, your instruments detect amino acids, fatty acid-like compounds, and complex hydrocarbons in some of the deeper ice layers. You feel the profound excitement of potentially discovering evidence that life has existed or continues to exist in the subsurface oceans that theoretical models predict should exist beneath the ice shells of many frozen worlds. The organic compounds appear to be distributed in patterns that suggest biological rather than purely chemical origins. They show isotopic ratios and molecular configurations that are difficult to explain through abiotic processes alone. You feel like you might be holding evidence of the first confirmed extraterrestrial life, preserved in the deep ice archives of this alien world. As you continue your surface exploration, you notice that the planet's weather systems are more active than expected for such a cold world. You observe ice crystal precipitation from the thin atmosphere, but the crystals have shapes and properties unlike terrestrial snow. The atmospheric ice formation processes create geometric patterns that look almost like natural art installations scattered across the landscape. The ice crystal precipitation appears to involve multiple nucleation processes that create crystals with different internal structures depending on the atmospheric conditions at the time of formation. You feel amazed by the diversity of ice crystal morphologies. Some look like tiny sculptures, others form chain-like structures, and still others create fractal patterns that seem to extend indefinitely at smaller scales. Your atmospheric monitoring equipment detects that the planet has a complex hydrological cycle involving sublimation, vapor transport, and redeposition of ice across different regions of the planet's surface. You realize that despite being a frozen world, Glacialis Prime has active water cycle processes that continuously redistribute material and create dynamic surface features. The weather systems appear to be influenced by the planet's geological activity, with geothermal areas creating local atmospheric circulation patterns that transport ice vapor and precipitate it in areas far from the heat sources. You feel like you're observing a planetary scale distillation process that separates and concentrates different chemical components across the planet's surface. As your first day of surface exploration draws to a close, you return to the landing site with sample containers full of exotic ice phases and potentially revolutionary discoveries about the nature of ice world geology and chemistry. You feel exhausted but exhilarated by the alien beauty and scientific richness of this frozen world that has exceeded your most optimistic expectation. Dr. Vasquez's preliminary analysis of your samples confirms that Glacialis Prime represents a completely new type of planetary environment where ice serves the same role that rock serves on terrestrial planets, but with chemical and physical properties that create possibilities for geological processes and potentially life forms. You spend the evening reviewing the day's discoveries and planning tomorrow's exploration routes. The surface mapping data suggests that there are many more exotic ice formations to investigate, including areas that might have direct connections to the subsurface ocean, where the most complex organic chemistry and potential biological activity would be expected to occur. As you prepare for sleep in your habitat module, you look out through the viewport at the alien landscape illuminated by the planet's auroras, caused by charged particles from the red dwarf star interacting with ice crystals in the upper atmosphere. You feel grateful for the opportunity to explore this beautiful and scientifically rich world, and you anticipate the discoveries that tomorrow's exploration might bring. The night sky above Glacialis Prime displays phenomena you've never seen before. Aurora curtains that change color as they pass through different ice crystal formations in the atmosphere. Meteor trails that interact with atmospheric ice to create temporary luminous clouds, and the strange optical effects created by the planet's multiple ice phases. You drift off to sleep, thinking about the implications of your discoveries for understanding planetary formation. The potential for life in extreme environments, and the possibility that ice worlds like Glacialis Prime might be among the most common habitable environments in the universe, even though they're completely unlike the warm, rocky planets that humans have traditionally considered suitable. Your dreams are filled with images of crystal palaces, flowing rivers of glass-like ice, and exotic life forms that might have evolved to thrive in the chemical richness and structural diversity of worlds, where ice rather than rock forms the foundation of geology. Weather and potentially biology in forms that stretch the boundaries of what you thought. You wake to the sound of your habitat's atmospheric processors working harder than usual, and you immediately notice that the external temperature readings have dropped significantly during the night. Looking out through the viewport, you see that the landscape has been transformed by what appears to be a heavy precipitation event involving multiple types of ice crystals that have created intricate geometric patterns across the terrain. The overnight weather system has deposited layers of different ice phases in distinct bands across the landing site, creating a natural laboratory for studying how various crystalline forms interact and transform under changing atmospheric conditions. You feel excited as you realize that this precipitation event has provided fresh samples of atmospheric ice formation processes that you couldn't have obtained through surface sampling alone. Dr. Vasquez's morning briefing reveals that the orbital monitoring systems detected significant geological activity during the night, including what appears to be a cryovolcanic eruption approximately 50 kilometers from your location. The event released large quantities of water vapor and dissolved compounds into the atmosphere, contributing to the unusual precipitation patterns you observed upon waking. You feel a mixture of scientific excitement and concern as you learn that the cryovolcanic activity indicates that Glacialis Prime has much more dynamic geological processes than initial surveys suggested. The planet's internal heat sources are apparently sufficient to maintain liquid water reservoirs beneath the ice surface, and these reservoirs occasionally break through to the surface in spectacular eruptions of superheated water and steam. Your second day's exploration plan focuses on investigating the cryovolcanic features and their relationship to the planet's subsurface ocean system. You feel anticipation building as you prepare your equipment for what might be an encounter with active geological processes that could provide direct access to the planet's deep chemistry and potential biological systems. The journey to the cryovolcanic site takes you across terrain that shows increasing evidence of recent geological activity. You observe fresh fracture systems in the surface ice, areas where different ice phases have been mixed and deformed by tectonic stress, and thermal vents that create localized atmospheric disturbances as they sublimate the surrounding ice formations. As you approach the cryovolcanic area, you feel the ground beneath your feet becoming less stable, with occasional tremors that indicate ongoing geological activity. Your instruments detect elevated temperatures just below the surface, and you realize that you're walking over a network of subsurface thermal conduits that connect to the planet's deeper heat sources. The cryovolcanic site itself is unlike anything you could have imagined. You see a complex of ice formations that appear to have been created by the rapid freezing of erupted liquid water, mixed with dissolved minerals and organic compounds. The structures rise like frozen geysers from the landscape, creating towering spires and delicate architectural forms that seem to defy the laws of physics. You feel amazed as you observe that the cryovolcanic formations are still actively growing through continued deposition from ongoing low-level eruptions. Warm water mixed with dissolved chemicals emerges from vents in the ice surface, flows for short distances in the frigid atmosphere, and then freezes into new ice formations with compositions and structures that reflect the chemical complexity of the subsurface source. Your instruments detect that the cryovolcanic eruptions are bringing to the surface water that has been in contact with the planet's rocky core for millions of years. The dissolved mineral content includes not only common salts and sulfides, but also rare earth elements and complex organic compounds that suggest active chemical processing in the subsurface ocean environment. The organic compounds in the cryovolcanic ejecta are more complex and diverse than those you found in the surface ice layers. You feel your pulse quickening as you realize that you're sampling chemistry that originates from deep within the planet, where conditions might support sophisticated biochemical processes, unlike anything found on Earth. Some of the organic compounds show tire preferences, molecular handedness that is difficult to explain through purely chemical processes and might indicate biological origins. You feel like you're handling evidence of life forms that have evolved in the dark, high-pressure environment of glacialis prime subsurface ocean, metabolizing the chemical energy available from rock-water interactions at the ocean floor. The cryovolcanic area also contains formations of exotic ice phases that require extremely specific pressure and temperature conditions to form. You observe what appears to be Ice X, a phase that normally exists only under pressures found in planetary cores, being deposited at the surface through rapid pressure release during the eruption process. You carefully sample the Ice X formations, knowing that this material will provide unprecedented insights into the physical conditions deep within ice world interiors. You feel like you're holding pieces of the planet's heart, crystallized evidence of the extreme environments that exist beneath the relatively benign surface conditions. The thermal vents associated with the cryovolcanic activity create localized ecosystems of chemical activity where different ice phases interact, dissolve, and recrystallize in continuous cycles. You observe that these areas have higher concentrations of complex organic molecules and appear to support ongoing chemical evolution that might represent the early stages of biological development. Your atmospheric monitoring equipment detects that the cryovolcanic area has its own microclimate with enhanced atmospheric density, elevated humidity, and complex circulation patterns driven by the thermal energy release. You feel like you're experiencing the planet's attempt to create more Earth-like conditions through geological processes that concentrate energy and materials in localized areas. As you work in the cryovolcanic area, you notice movement in some of the thermal vent regions that doesn't appear to be purely physical or chemical in origin. The movement patterns suggest organization and response to environmental stimuli that might indicate primitive biological activity adapted to the extreme ice world conditions. You carefully approach one of the active thermal vents and deploy specialized sensors designed to detect biological signatures in extreme environments. You feel your heart racing as the instruments begin registering patterns of chemical activity that show the hallmarks of metabolic processes, organized chemical reactions that maintain themselves and respond to environmental changes. The biological activity appears to involve organisms that utilize the chemical energy available from dissolved minerals and organic compounds in the vent fluids. You realize that you might be observing the first confirmed extraterrestrial life forms, evolved to thrive in environments where liquid water exists under high pressure beneath kilometers of ice. The organisms, if that's what they are, appear to form complex communities around the thermal vents, with different species occupying different chemical and thermal niches within the vent environment. You feel amazed by the apparent sophistication of these biological systems, which rival Earth's deep-sea hydrothermal vent communities in their complexity and organization. Your microscopic analysis of water samples from the active vents reveals structures that appear to be cellular in nature, but with architectures unlike any terrestrial life forms. The cells use exotic biochemistry involving silicon-carbon hybrid molecules and appear to maintain their organization through processes that operate at temperatures well below the freezing point of normal water. The discovery of active biology in Glacialis Prime's thermal vent systems revolutionizes your understanding of the potential for life in ice world environments. You feel the profound excitement of realizing that frozen worlds might not be barren ice balls, but actually represent one of the most common types of habitable environment in the universe. Further investigation reveals that the biological communities extend deep into the subsurface through networks of fractures and cavities in the ice formations. You realize that the entire planet might have an extensive biosphere based on chemosynthetic metabolism that operates independently of solar energy, sustained by geological processes and chemical energy sources. The biological systems show evidence of complex ecological relationships, with apparent predator-prey dynamics, symbiotic associations, and competitive interactions, similar to those found in Earth's ecosystems, but operating through completely different biochemical mechanisms adapted to the ice world environment. Your sample analysis reveals that the organisms produce complex organic compounds that are incorporated into the planet's ice formations, creating a geological record of biological activity that extends back millions of years. You feel like you're reading a book of life, written in crystalline ice, rather than fossil rock, documenting the evolution of biology under conditions completely alien to Earth. The discovery of extensive biological activity forces you to reconsider everything you thought you knew about the requirements for life and the distribution of habitable environments in the universe. You realize that ice worlds like Glacialis Prime might actually be more suitable for supporting complex ecosystems than the warm, rocky planets that humans have traditionally considered most habitable. As your exploration of the cryovolcanic area continues, you discover that some of the biological communities appear to influence the geological processes around them, modifying the chemistry of the thermal vents and affecting the types of ice formations that develop in their vicinity. You're witnessing a form of biogeochemical evolution where life and geology co-evolve in feedback loops. The organisms appear to use sophisticated mechanisms to control their local chemical environment, precipitating specific minerals, concentrating useful compounds, and modifying pH and redox conditions to optimize their metabolic processes. You feel amazed by the level of environmental engineering these simple organisms can accomplish through their collective activities. Your investigation reveals that the biological communities have created complex, three-dimensional structures within the ice formations, building what can only be described as cities of living ice, where different species create specialized microenvironments for their particular metabolic needs. The biological architecture shows evidence of planning and cooperation that suggests these organisms might have more sophisticated information processing capabilities than their simple cellular structure would suggest. You begin to wonder whether you're observing the early stages of collective intelligence emerging from communities of simple organisms. Some of the biological structures appear to serve as communication networks, transmitting chemical signals across large distances through the ice formation matrix. You realize that the entire cryovolcanic area might function as a single, interconnected biological system. With information processing and decision-making capabilities distributed across millions of individual organisms. The implications of your discoveries extend far beyond astrobiology into questions about the nature of intelligence, consciousness, and the possible forms that advanced civilizations might take on ice worlds. You feel like you're glimpsing possibilities for non-technological civilizations that achieve sophistication through biological and biochemical engineering, rather than mechanical technology. Your exploration takes you to areas where the biological activity appears to have created large-scale modifications to the planet's ice geology, including formations that serve as solar collectors, atmospheric processors, and chemical concentration systems that enhance the habitability of the ice world environment. You begin to suspect that what you initially interpreted as natural geological processes might actually be the result of millions of years of biological engineering by organisms that have learned to shape their planetary environment to better support their continued evolution and expansion. The evidence suggests that Glacialis Prime might be an example of a biologically terraformed world where indigenous life forms have gradually modified the planetary environment over geological time scales to create conditions more suitable for supporting complex biological communities. This realization forces you to reconsider the relationship between life and planetary evolution, suggesting that biological processes might play a much more active role in shaping planetary environments than previously suspected. You feel like you're discovering principles of planetary biology that could revolutionize understanding of how worlds become and remain habitable. Your final day of surface exploration focuses on mapping the extent of the biological modifications to the planet's ice geology and attempting to understand the long-term evolutionary trajectory of the ice world biosphere. You feel like an archaeologist studying the remnants of a vast biological civilization that operates on geological timescales. The evidence suggests that the biological systems on Glacialis Prime are approaching a critical transition point where their collective activities might enable them to begin modifying the planet's atmospheric composition and thermal balance, potentially triggering a transition to a more temperate climate state. You realize that you might be witnessing a planet in the process of biological terraforming, where indigenous life forms are gradually transforming a frozen world into something more suitable for supporting even more complex forms of biology. The implications for understanding planetary habitability and the search for life in the universe are staggering. As you prepare to depart from Glacialis Prime, you take one final look at the alien landscape that has revealed so many secrets about the potential for life in ice world environments. You feel changed by your encounter with this frozen world and its sophisticated biological systems that challenge every assumption about the requirements for habitability and the possible forms that life and intelligence might take. The return journey to Earth will take several months, during which you and Dr. Vasquez will continue analyzing the samples and data collected during your exploration. You know that your discoveries will revolutionize astrobiology, planetary science, and humanity's understanding of its place in a universe that appears to be far more alive and creative than anyone previously imagined. Your samples contain direct evidence of extraterrestrial life, exotic ice phases that demonstrate new states of matter, and organic compounds that suggest biochemical processes unlike anything found on Earth. You feel the weight of responsibility for communicating these discoveries in ways that will advance scientific understanding, while preparing humanity for the profound implications of discovering life beyond Earth. The journey home also provides time to reflect on the philosophical implications of your discoveries. The existence of sophisticated biological systems on ice worlds suggests that life might be a much more common and resilient phenomenon than previously believed, capable of thriving in environments that seemed completely hostile to biological processes. You begin writing your mission report, knowing that it will describe discoveries that will be studied and debated for generations. The evidence from Glacialis Prime suggests that ice worlds represent a major category of habitable environment that might actually be more common and more suitable for supporting complex life than Earth-like planets. The implications extend beyond astrobiology into questions about the future of human space exploration and the possibility of establishing colonies in ice world environments. Your discoveries suggest that ice worlds might offer resources, energy sources, and even biological partners that could support human expansion into the outer solar system and beyond. As Earth grows larger in your viewports during the final approach, you feel grateful for the opportunity to have explored one of the universe's most alien and beautiful environments. The frozen landscapes of Glacialis Prime will remain with you forever, along with the knowledge that life has found ways to thrive in conditions that seemed impossible. Your return to Earth marks the beginning of a new era in humanity's understanding of life, habitability, and the incredible diversity of environments where biological processes can operate and evolve. The strange science of planets made of ice has revealed that the universe is far more alive, creative, and full of possibilities than anyone dared to hope. The samples and data from Glacialis Prime will fuel decades of research that will reshape scientific understanding of planetary formation, astrobiology, and the potential for life throughout the universe. You feel honored to have been part of the mission that discovered that ice worlds are not frozen wastelands, but dynamic, living worlds that might represent the most common form of habitable environment in the cosmos. Your discoveries on Glacialis Prime demonstrate that the universe is full of worlds where the familiar becomes alien and the impossible becomes routine, where ice can flow like rivers, life can thrive in conditions that would instantly kill Earth organisms, and planetary scale biological engineering can transform entire worlds. The strange science of ice worlds has opened new chapters in humanity's exploration of the cosmos, revealing that life, creativity, and intelligence can emerge in forms and environments that stretch the boundaries of imagination, while demonstrating that the universe is far more hospitable to life than anyone previously believed possible.